Okay, so with all that being said, hopefully you guys agree that this is a worthwhile skill. We're going to need this. We need to know how to balance equations in order to do anything in our unit. I've already shown you one method. The method is balancing reactions using the standard table. And so I didn't want to read through all of the steps, but I mean, isn't what we just did on the board something like this? Split the equation into two half reactions. You know how on the far board over there I have one that says R, one that says O? I found the two half reactions, right? I wrote them out, one for reduction, one for oxidation. Then if the number of electrons was not the same, we do some multiplication. Then we add the two half reactions together, and then we just double check if we want to. So this is one method. So why don't we do an example on this, a second example. Right, if I give you a scenario like this, let's say that we can write and balance our equation. So we've got the dichromate ion is a good oxidizing agent. It reacts with tin in an acidic solution. So the first thing you're going to want to do is go to your data table. I'll just draw one out kind of pretend-wise. We got to circle everything we've got. So first we need to look for the dichromate ion, Cr2O7. It is relatively high on the left-hand side, I believe. So like the sixth one from the top or something. It's right about here, Cr2O7. It also requires 14 H pluses, though. Can you guys find that one? Well, we have the Cr2O7. Do we have the 14 H pluses? Yeah. Because you know how it said it reacts with it in a acidic solution? I mean, in theory, that means we also have the H plus that's right in the middle of the table. We probably could also use water that's way down here. Here's the other thing, though. It reacts with a tin-2 ion. Tin-2 ions are found, let's see, there's one right about here. There's an SN2 ion right there. Where's the other tin-2 ion? There it is, yeah. So right above it, right about there, SN2+. There is the other tin ion. In theory, you could probably also put the water that's up here. But once you get the idea of it, now that I've labeled where everything is, this is a beaker stuff question. There's like 6 different things here. We got to figure out who's going to react. You guys are probably ahead of me, right? This is going to react with this because it's spontaneous. So all you got to start doing is writing out your equations. So equation 1. The reduction equation is Cr2O7 2 negative, and you need one of those. You need 14 hydrogens. You need 6 electrons. That's kind of new. And then this turns into 2 chromium 3 plus ions and 7 waters. So this is equation 1. And then for your oxidizing equation, you have to make sure you write the tin equation going the other way. You have to write it going backwards. So that would be your tin 2 plus oxidizing going backwards and forming tin 4 plus and 2 electrons. Sound good? Do the electrons match? Clearly not. Here there's 6, there's 2. Do you guys understand why I taught you Hess's law before I taught you this unit, though? There's actually some strategy into which unit goes first. This is Hess's law. We're then going to take the entire second equation here, triple it all. Now the electrons do cancel, and now we're good to go. So here's your final equation. Cr2O7 aqueous plus 14 hydrogens aqueous plus 3 tin 2 pluses aqueous, and it turns into 2 chromium 3 pluses, 7 waters, and 3 tin 4 pluses. That's your equation. It's a little more challenging than a typical grade 8 equation, isn't it? Or not grade 10 equation, right? This is not single double replacement anymore. This is kind of fitting into its own category. The good news is that when you're balancing equations, you always know when you're right. because you should be able to check. You got to check two things. Okay. From a physics point of view, for those of you, the four of you guys who took physics last, remember how there were those 10 laws that were written on one side of the periodic on the table? Law of conservation of mass is one. Law of conservation of charge is another, right? You have to make sure that both of those things don't get broken. So first do law of conservation of mass and make sure that species on both sides are the same. So like I see 2 chromiums to 2 chromiums, 7 O's to 7 O's, 14 H's to 14 H's, and 3 tins to 3 tins. But this is the more important thing I got to point out. Law of conservation of charge still has to hold. Okay? Because not everything here was a neutral compound, if you begin with a certain amount of positive or negative charge, you better end with the same amount. So let me walk you through that bit. See how there's -2 right here? And there's 14 positive, and 3 by 2, 6 more positive. There is a grand total of 18 positive on this side over here. Can you guys follow that math? This is 14. That's 6 more. That would have been 20 positive. But I'm bumping it back 2 because there's 2 negative right here. So this entire starting side began with an 18 positive charge. By this logic, this other side here better also have 18 positive on it. If not, then we broke the law of conservation of charge. So there's 6 positive right here. And then this was 3 by 4. That's a 4, by the way, which is 12 more. 6 and 12 does actually add up to give you 18. So we're good. Does that make sense? Okay, good. But that's only level 1. We got 3 more examples to show you. That one's nice. And the reason why it's nice is because everything was in your data booklet. What happens when, I'm not just saying if, but I'm saying when they give you a question and they throw something at you that's not in your data booklet? Well, we need to be able to find a way to work around that. They're going to be jerks. Okay. And so I need you guys to be able to balance redox equations in both acidic and basic solutions. And that's kind of what our next 2 examples are about. Rather than read all this, I'm just going to go right to the example here. It says aqueous dichromate ions react with nitrous acid in acidic conditions to produce the nitrate ion and chromium 3 ion. Do the same thing that we tried to do before. Grab your data booklet. I'll just write it off to the side here. And let's start circling some stuff. It said we need dichromate ions. Well, we just did that one, right? So that's our Cr2O7, 2 negative. We got that one. And it reacts with nitrous acid. What's nitrous acid? HNO2. Now, I don't expect for you to find an HNO2 directly on your table, but you could ionize that into an H plus and an NO2 negative. H plus, we've already been there. Find me NO2 negative. Yeah, Darian got my point. They could throw something at you that's not on the table. Okay, just so you guys are aware, this table is not literally everything known to humankind. This is like a most common table, but there is more available than just what's listed on this table here. So because of the fact that NO2 negative not being on your table, it rules out that whole idea. And yet we should still be able to write the equation. So let me walk you through some steps as to how to do this. The first thing you're going to want to do is you're going to want to write basically what we call the skeleton equations of your oxidation and reduction half reactions. Okay? We don't use the term skeleton reaction all that often, but I mean, essentially, it's just the very, very basic amounts. We haven't even gotten to everything else that's there. So I'm going to write out some really basic concepts. It says that we start with dichromate ions. So I'm going to start by writing that. Dichromate is Cr2O7 with a 2 negative charge. And it said that dichromate is eventually going to turn into the chromium 3 ion. So I'm going to use purple to help keep this together. So I know kind of the basics of it. It's going to turn into the chromium 3 ion. I'm going to use another color here. It also says that nitrous acid, so that was the HNO2, it says that it's going to turn into the nitrate ion, which is an NO3 negative. So this right here, this is me writing some skeleton equations. At least I'm starting to. I took what they gave me in the blurby above, and I'm writing out what seems logical. I mean, it does seem logical, by the way, that the chromium dichromate turns into chromium, the nitric turns into that. It wouldn't make sense for that one to turn into that, right? Is that clear? All right, now one of the things that we can assume is that because I wrote aqueous solutions nearby, that water and its basic and acidic components are something we can use to help us balance. Okay. So we can actually utilize water as part of our equation. Let me look at the top equation right here. First of all, right off the bat, is the chromium itself actually balanced? See how there's 2 chromiums right here? How many chromiums am I currently writing? Okay, well here, that solves that problem. So right off the bat, I'm going to actually balance like chromium itself. But law of conservation of mass is clearly being broken because isn't there 7 oxygens over here? And on this side of the equation, there's not 7 oxygens? Well, there's actually a really easy way to fix that. Remember how I said a few seconds ago that these are in aqueous solutions? Water itself could be a reactant. Or why don't I make it be a product? I'm going to put 7 waters on this side right here. Why did I put 7 waters on that side there? What am I trying to balance? Oxygen. You see how right here you had 7 O's right here? I can't just have 7 oxygens just magically disappear. But you know what's very logical is, well, what if those 7 oxygens somehow turned into making us some more water? That's reasonable. Right? Many of the reactions that are on our table involve water. So now I found a way to make this oxygen here balance those oxygens there. Only in the meantime, I've actually made myself a new issue. Sure, chromium's now balanced. Oxygen's now balanced, but what did I now introduce into the equation? But actually, there's an easy fix for that. I'm going to throw 14 hydrogens onto this side over here. Remember how I said it was in acidic conditions? Well, if it was under acidic conditions, I could have 14 H plus ions on this side. There. Now I've actually balanced the acidic part of this. So chromium's balanced, oxygen's balanced, hydrogen is now balanced. There's only one last thing we need to balance, actually. Charge. Always have to consider charge. Because right now, am I showing any electrons being gained or lost? Not yet. So let's do a quick charge calculation. There's 14 positives plus 2 negatives. So this side right here currently has 12 positive. Does that make sense? And then the right-hand side over here currently has 6 positives. I can't have 12 positives turn into 6 positives. I need electrons. So the answer is I need to put 6 electrons on this side. Why on the left side, not on the right? Can I make something become more positive? No, because I can't add more protons. But you know what I can do? I can use electrons and bring the positive down. So if I add 6 more electrons to this side, then that's really knocking this back down to 6 positive. Now is the charge balanced? Yeah. What have I written, an oxidation or a reduction equation? There's only 2 choices, oxidation or reduction. Think it through. Leo says GR. Am I losing electrons in this equation, or am I gaining electrons in this equation? Okay, well, if I was losing electrons, which side of the equation would we write the electrons on? If electrons were on this side here, we'd be losing them. So because the electrons are written on this side right here, you must need to gain electrons. So based on this, I now know that we are gaining electrons to reduce. So this is my reduction equation. See why I'm beating this terminology into your head? You really have to know which one is which. Okay, let's try the exact same thing on the second equation. This half reaction down here, if the top one's the reduction half, this bottom one better be the oxidation. Let's try the same thing. Are our nitrogens currently balanced? Yeah. Because you know on the top equation, chromium wasn't. Well, nitrogen is balanced. Is our oxygens balanced, though? No. But I can fix that. Don't forget, this is aqueous solution, right? Aqueous solution means that, well, why can't water be not only just the solvent, but also the reactant? So why don't I add a single water onto this side right here? Well, now the oxygen's balanced, right? There's 1, 2, 3 to 3. Okay, well, if I added some random waters on one side, don't forget this was in an aqueous solution, which was acidic. So I can account for that by adding hydrogens. So see how there's 3 hydrogens over here on the left-hand side? Let's add 3 H pluses over here. That should take care of the hydrogen problem. Okay, so double check here. 1 nitrogen to 1 nitrogen. 1, 2, 3 oxygens to 3 oxygens. 1, 2, 3 hydrogens to 3 hydrogens. But what have I also missed? Charge. Now, before I even get into this here, I know which side the electrons better be on when I'm done. If the electrons over here were on the gaining electron side, then they better be over here. Right? Otherwise, I've done something wrong. So this is neutral and that's neutral, so really you need no charge on this side over here. Over here you have 1 negative, you have 3 positives, which is a net of 2 positive. So how many electrons do I need? 2 electrons on this side. Okay, we're almost done. I now have my 2 equations written. This one is my oxidation one. This one's my reduction one. This is why it's so critical for me to teach you Hess's law first. Because not only are there going to be electrons on both sides, there's also going to be water and hydrogen on both sides. But I'm not quite there yet. What else do I have to do first? Before I start Hess's lawing this thing, what needs to be equivalent? The charge, yeah, the electrons. See how this guy has 6 electrons right here? This reaction down here only has 2. So I need to take the whole bottom reaction and I need to triple it by putting a 3 here, a 3 here, a 6 here, a 3 here, and a 9 there. Now I'm ready to add it all up. Okay, let's start with the stuff that I only have 1 of. There's only a single Cr2O7, so I'll start with that. Cr2O7, 2 negative, aqueous. I need 1 of those. I also need to put down the nitrous acid, so I'm also going to need to have 3 HNO2s. And over here, I'm going to do the 2 Cr3 pluses. And I'm going to do the 3 NO3s. And the reason why I started with those is because there's only, I know the coefficient might not be 1, but there's only 1 of them to consider. Because everything else there's 2 of. 1 on the reactant side, 1 on the product side. I'm going to have to add or subtract. Taking care of this one, that one, and this one. Now I'm going to do the electrons. There's 6 electrons on both sides, so that's perfect. They should cancel. What about water? 7 on the right, 3 on the left. What's my net? 4 over here, right? 7 and 3 nets me 4 over on the product side. What about my hydrogens? There's 14 here and 9 there. 14 and 9 leaves you with a net of 5 on this side here. And I think I've now covered everybody. So I know this is a bit different way of me writing it, but this should be my net balanced equation. Walk through that one more time then. I lose you somewhere. Okay, so this one I just wrote there. This one I wrote there. And this one I wrote there. This one I wrote there. And then I considered the things that there's more than 1 of. Like say, let's take water. Say there's 7 waters on one side, but 3 on the other. Well, think of it like algebra, right? When you bring this to the other side, there's only going to be 4 left on this side right here. And then in the same algebraic way, if you've got 14x on one side and 9x on the other side, if you bring this to the other side and kind of cancel it, there's only 5 hydrogens left over. Does that make sense? Okay. Last thought here. Let's double check to make sure it truly is balanced. So we should consider not only the species themselves, but also consider their charge. So 2 chromiums to 2 chromiums, 7 plus 6 oxygen gives 13 oxygen. Right here, there's 9 oxygen, and 4 more. 9 and 4 is actually 13. Oxygen's a good. There's 3 plus 5 hydrogen, which is 8. And look, there's 8 over there. I see 3 nitrogen and 3 nitrogen. I think all the species are balanced. But most importantly, charge better be balanced as well. So we have 2 negative right here and 5 positive, which leaves a net of 3 plus on this side. This side over here better also have a net of 3 plus. And you've got 6 plus right here and 3 negative right here. So yeah, it also has a net of 3 plus. So everything's balanced. This is a bit trickier than your standard grade 10 balancing equation though, isn't it? Because what's challenging about this one is that we actually had to write in our own equation. Our equation involved this stuff and this stuff right here that was stated above. It mentioned dichromate. It mentioned nitrous acid. It mentions a nitrate, and it mentions chromium. But you know what we needed to fill in the blanks with? We needed to fill in the blanks with some H pluses and some waters. Which makes sense, though, because it mentioned that it was in acidic solution conditions, and it mentioned that it was aqueous. So I'm not overly surprised to see water and H plus be a part of my equation. That's not a huge surprise. But that's the extra thing we need to now add in. Make sense? Okay, let's try another one. Well, if you can do something in acidic solutions, you can also do it in basic solutions. Now, just so you guys are aware, if you read through all my steps, many of them are the exact same. But we kind of change things at the end to do with the acidic part. So I'm going to do the same thing as always, though. I'm just going to hop right in. We're going to give this one a try. You guys can read through the steps later if you like. Okay, it says we have solid chromium 3 hydroxide, and it reacts with aqueous chlorate ions to produce chloride ions and chromate ions. Right off the bat, we could try to use our table. You guys are more than welcome to go take a look, but it may just be best if you just try to write it yourself, because you might not find everything we're looking for there. So I'm going to start with step 1. I'm going to start writing a skeleton equation of like what logically turns from one thing to the other. I see right here you have chromium turning into chromate. That seems logical, doesn't it? And then for the other reaction, I see chlorate turning into chloride. I think that seems like the most logical starting spot. Is hydroxide going to be a part of it? Yeah, I bet you to balance the O's and H's, somewhere along the way, hydroxide matters. But let's just start with this. And I'm going to do my best to try to keep these simultaneously like side by side. So I'm going to do this. I'm going to do Cr3+. That's my chromium. And I'm going to turn it into chromate, which is Cr O4 negative. I use chromate a lot. Is it 2 negative or 1 negative? 2 negative? Is it 2 negative? Chromate. Yeah, it is 2 negative. Yeah, you're right. Should have trusted you. Okay, and then why don't I try to do this at the same time going down? I'm going to take some chlorate, which is ClO3 negative, and I will try to turn it into chloride ions, which is going to be Cl minus. One of these will be the oxidizing reaction, one will be the reducing reaction. Yes. This one right here, this Cr3+. Because it said we had chromium 3 hydroxide. And so chromium 3 hydroxide would be CrOH3. And so I'm just picking the chromium part of that and figuring out that the chromium 3 is probably turning into chromate, which is this bit right here. And then I'm saying that the chlorate is going to turn into chloride, which is where the blue part came from. Does that make sense? So like I just went through with my colored pen and I just picked out the basics to write my skeleton equation. This looks like it's turning into this, and this looks like it's turning into that. You have a question? Well, I'm not ready for it yet. I'm going to throw it in later. You know how it mentioned that like it was in a basic solution? This hydroxide will probably come up later, but I'm just going to start with the skeleton equation, okay, just to get going. I will get to the hydroxides in a bit, though. Like, it will happen. Okay. Let's try working with this one here first. Isn't the chromiums balanced? Yeah. One chromium to one chromium. Here's why we're going to need hydroxides, though. Is the oxygen balanced? No. There's 4 oxygens over here. I need oxygen on this side right here. Well, it's actually best if you just do what we did last time. To try to figure out the oxygens that go over here, why don't I make this 4 waters on this side here? Wouldn't that account for the 4 oxygens we need? Okay, but now I have 8 hydrogens on this side. I don't want the 8 hydrogens on this side. What did we do last time in acidic conditions? Well, we added 8 hydrogens to this side. Here's the problem, though, and I think maybe this is what you were noticing earlier, Rebecca, when you asked about the hydroxide. Now's the time for the hydroxide. This was supposed to be in basic conditions, but this is clearly in acidic conditions. So is this balanced right now, though? Like minus the electrons is the species balanced. 1 chromium, 1 chromium. 4 oxygens, 4 oxygens. 8 hydrogens, 8 hydrogens. It's balanced, right? But maybe here's a better way of approaching this thing. What if I were to break this water up into something like, say, 4 H pluses and 4 OH minuses? What if I wrote it like that instead? Would that make sense? Like how I could take my 4 waters and I could break it up into equal parts acid and base there? Well, now I can work with my hydroxides. The problem is, though, if I try to do that, see how I could like start to cancel these hydrogens on both sides here? Does it exactly cancel? Not yet. So I got a trick for you. But I want to illustrate this to try to show the idea that I can make a hydroxide show up, right? You asked a few minutes ago, where's the hydroxide? Here's the hydroxide. The problem is it's the wrong number of hydroxides. So I want to go back a couple of steps here. And what I want to do is this. You know how in algebra you can add something to both sides of an equation and it's considered valid? Okay. What I'm going to do here is now that I've got to this point here where it's balanced, I'm going to add 8 hydroxides to this side and 8 hydroxides to this side. Adding 8 hydroxides to both sides, that's valid because I'm doing it to both sides. What happens, though, when you take 8 hydrogens and add 8 hydroxides to them? What have you really made right here? Yeah, you've actually made the opposite of what I showed you earlier. You've actually made 8 waters. So now this stuff right here, I can really consider to be 8 waters. But hang on. Isn't there 4 waters on this side? To 8 on this side? So can I do some canceling? If there's 4 here and 8 here, couldn't I get rid of these 4 right here and say that I just have 4 here? Let's take stock of what we did. I'm going to have to do that again. But let's take stock of what we've got now. Are my chromiums balanced? Yeah, 3 chromiums to 3 chromiums. Are my oxygens balanced? It's a little more tricky to look at, but there are 8 oxygens over here, and there are 4 plus 4 oxygens over there. Yeah, oxygens balanced. There's 8. Are my hydrogens balanced? There are 8 hydrogens right here, and there are actually 8 hydrogens right here. But now I've solved the problem Rebecca mentioned earlier, which was, hang on, what happened to the hydroxide? Boom, there it is. So, can I show you that one more time? Because that's... Now, I've got all the steps written out, by the way, on the previous slide. But let me show that one more time from the top here. So I'll take it from here. Okay. Here's hopefully the logic you go through. There are 4 oxygens on this side right here, and this side has no oxygen, so I'm going to add 4 waters. That'll account for the 4 oxygens I need. The problem then, though, is that now there's 8 hydrogens on this side, so why don't I put 8 hydrogens on this side? Again, solves that problem. Good point here. I really shouldn't, because it was an acidic solution, right? But this is probably the easiest way to like demonstrate how to balance it. Because if I try to add hydroxides to one side, here, let me give you this example here. Oh shoot, I'm too far back. Let's say I try to add hydroxides. Say I add 4 hydroxides on this side right here. Okay, well now the O's are balanced right here and here, right? But now I have hydrogens. Well, I can't use H plus to balance, right? So if I try to use water, I can try to throw some water on this side. Let's say I threw 2 waters on this side. Well, now the 4 hydrogens are balanced. The 4 hydrogens are balanced, but you know what I just messed up? Your oxygens. Do you see how you're going to be in a never-ending loop between this one to this one, trying to balance those guys? So the strategy is, rather than trying to, back here, add hydroxide to one side, we're going to get there. We know that's happening eventually. What works really nicely is add 4 waters to this side. When you add the 4 waters to this side, add 8 hydrogen to this side. I know that that's not correct, but bear with me for just 1 second. Then we're going to play a little algebra kind of trick where I'm going to put 8 hydroxides on both sides. That's fair. You're putting them on both sides equally, right? What ends up happening is these 8 hydroxides and hydrogens are now really 8 waters. And then these 4 waters and 4 of those guys then cancel. And now I've written myself an equation that works, and there's a hydroxide on this side here. You want to try this a few times, obviously. There is one thing I haven't done yet still, actually, for the green reaction. What else haven't I included? Electrons. Okay, so on this side right here, I have a net of -5. And on this side right here, I have a net of -2. Let me show that one more time. You have 3 plus right here, and 8 negatives, so that's -5. And on this side right here, you just have this -2. Which side do electrons need to go on, and how many? Say it. How many? I'm sure you have it. Okay, you need 3 electrons. Do you need the electrons over here or here? You need them on this side here, yeah, because we need to add 3 more electrons. Because now 3 negative and 2 negative does make the 5. So my chicken scratch right here is this, 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 that, and that. These are the 5 things that are part of my equations. I'm going to use that with the blue one in just a second. So let's try the exact same thing in blue now. Time. That's okay. Step 1. Are my chlorines balanced? Okay. Are my oxygens balanced? Okay. Now we could try adding hydroxide to one side, but that makes it a mess. It actually works better, I promise you it does, okay, to add water. So let's put 3 waters on this side right here. Because if I put 3 waters on this side here, your 3 oxygens, they balance. Okay, well, now to make up for the hydrogen you just added here, you've added 6 hydrogens to the right side, right? So let's add 6 hydrogens over here, which I know is wrong because it was actually in a basic solution, not an acidic solution. But at the very least, now my species are balanced. Chlorine with chlorine, oxygen with oxygen, hydrogen with hydrogen. Quick little fix then. Let's add 6 hydroxides to both sides. That seems fair, right? If I do it to both sides, it's equivalent. Why am I doing that? Yeah, because it not only gets rid of my hydrogens over here, but it turns these guys into 6 waters, which means I don't even need you anymore. And see how there were 3 waters and 6 waters? I can then cancel this guy out and just say that there's only 3 of these left. I now should have written myself a balanced equation, minus the electrons, but this should now be balanced, right? 1 chlorine, 1 chlorine. 3 plus 3 more oxygens makes 6. And 6 hydrogens with 6 hydrogens. We're perfect. And, better yet, is this in a basic solution? Yeah, because now we've actually produced hydroxides. Last step, we need electrons, though. This guy over here needed to lose electrons. Hopefully it's clear by putting the 3 electrons on the right side, that's losing electrons. So I'm expecting to put electrons on the gaining side over here. Let's try it. We've got 1 negative on this side right here. And then here you've got 1 plus 6 more, which is 7. So I need 6 electrons on this side here. Solves that problem. It's not exactly in the typical way of writing things, but I've got products and reactants for reaction 1. And I've got reactants and products, there you go, and reactants and products for reaction 2. And all I've got to do is just try to sum everything up. In order for it to work, though, the electrons have to balance. Are the electrons currently balanced? There's 3 in this column and 6 here. So I'm going to have to take everything in this reaction here and double it. Not just the products column, but everything. So I'm going to make this a 2. This is going to be a 16. This will become a 6. This will be a 2. This was all canceled anyways. And you're upgraded now to an 8. Let's put it all together. The most important thing, you need to have an organizational scheme that works for you. You need to try to a good way to keep track of where all your stuff is. Because you're going to be doubling equations and tripling them and adding extra waters on different sides. So now I want to sum everything up. I'll start with my reactants. I have 2 chromium 3 plus as a reactant, so I'm going to start with that. And in terms of other reactants, I also have the ClO3, so I'll write that one out as well. The ClO3 negative, it's a reactant. So that accounts for this guy here and that one there. There are other reactants I should consider, but I know some of them are going to cancel, so I'm going to deal with that part later. Now let's do products. There's going to be a 2 CrO4 needed. CrO4 needed. That accounts for this guy. And we're also going to need to have a Cl negative needed. That accounts for this guy. So I've done this one. I've done this one. I've done this one. I've done that one. Now I want to consider the rest. The electron should cancel, right? This electron should cancel that one there, so that takes care of that. Let's do water next. How many waters are left over, and on what side? How many waters are left over? 5. And on what side? You have more products than you have reactants, so you need to have 5 more water products. Because these 8 water right here will cancel with these ones here, and leave you with a net of 5. And then lastly, we also need to consider our hydroxides. There are 16 and 6 on each side, so clearly there's 10 left over. 10 on the reactant side, so 10 hydroxides here. And I think we're now finally done. This sucks, eh? It does. It really does. It is not a short question if you get asked to balance something in acidic or basic solutions. But hopefully, let's just do a quick double check. 2 chromiums, 2 chromiums. 3 plus 10 makes 13 oxygens. This was 8 plus 5. That does make 13 oxygens. There's 10 hydrogens, and 5 by 2 is 10 hydrogens. So all of my species are balanced. Oh, 1 chlorine to 1 chlorine. Now for the charges. There's 3 positive times 2, so that's 6 positive. Then there's 1 negative and 10 more negative, which leaves a grand total of, 5 negative as your net charge here. And then on this side right here, lo and behold, 2 times 2 gives 4 negative. 1 more negative and a neutral does give 5 negative. So yeah, this is your balanced equation. Yay! Okay, I have 10 minutes left. there is a likely chance that you will not have to do this in the diploma. Okay. I don't see this regularly. Okay. I will tell you this. There is always at least something for balancing. Okay, that is literally one of the outcomes. Students will know how to balance redox equations. This is your like in case of emergency break glass method. If you have something that you're trying to balance and it is such a pain in the butt that you cannot figure out how to do this, hopefully what I've now shown you is a very step-by-step, sequential method that should always work. But I have to let you know, you don't always have to do it that way. Okay? Sometimes when they give you the equation to balance, you will just literally look at it and go, well, put a 4 there, put a 2 there, it does it. And honestly, if you can just do that, do that. You know what I'm saying here? So what I'm trying to do here today is I'm trying to give you tools in case you need them. But I sincerely hope that we don't actually have to do that method because it is a pain. I want to do one last example here. And I should be able to do this in 10 minutes or less here. Where this is the one I gave you. You guys have this one here as your last slide? Where if you want to, you can probably just look at it and balance it. Okay? You could try the method that we just did before. Let me walk you through what you would do if you tried the previous method. You would write out in blue H3ASO3 and have it turn into H3ASO4. Don't write this by the way. In green, you would write out HNO3 turning into NO. Then you would add 2 waters on this side. You would add 3 H pluses on this side. And you would add 3 electrons. And over in the blue equation, you would add 1 water to this side. And then you'd have to add 2 H pluses to this side and 2 electrons. Like you'd have to do something like this. It would work. It would suck, but it would work. But honestly, if you can just see it and figure out how to balance it, that works too. And sometimes that's your best option is just take a few minutes, try a few things, and do that though in conjunction with this trick I want to show you. It involves using oxidation numbers. You guys remember doing oxidation numbers before we left last week? It's basically the whole assign a number to everything concept. The basic rules are hydrogen is always +1. Oxygen is always -2. And we should be able to figure out the rest by just using some like common sense, I guess. So the leftover bit on this nitrogen here is +5. Is that clear? I'm going to go over to this nitrogen over here. This nitrogen over here, though, better be +2. Clearly, nitrogen has changed. That's the whole point of oxidation numbers. How much has oxygen changed? Sorry, how much has nitrogen changed by? What happened to it? Did it gain or lose electrons? It did. It gained 3 electrons. Daniel, you're right. It gained 3 electrons. All right, let's try the other thing I didn't put up there. Let's try the arsenic. This one's going to be a challenge. Okay, so we've got 6 total negative right here, and then 3 total positive right here. Does it make sense to everybody that this arsenic going to be a +3 to make that fit? Now let's go over here. Here, there's 8 total negative and 3 total positive, so this better be a +5. Based on this, how do you go from a 3 to a 5? Yeah, you have to lose 2 electrons. With that information, that may be enough to get you started on just balancing just by looking at it. Just by looking at it now, you might be able to just say, I think I know where some numbers go. If this guy gains 3 electrons and this guy loses 2 electrons, does that mesh nicely? What's the lowest common multiple of 2 and 3? 6. So the logic would be that the lowest way this can work is that I'm going to need to times this by 2 to get me 6. And I'm going to need to times this one here by 3 to also get me 6. And here's how I do that. I'm going to take this whole equation here. I'm going to put a 3 in front. And I'm going to take this whole equation right here. I'm going to put a 2 in front. And now I'm just going to look at it and try to balance it. And if it works out properly, I should just be able to look at it and have it work. So, right, this 2 times 3 should have a 6 electron change. This 3 times 2 should also have 6 electron change. Let's try it. I'm going to start by looking at nitrogen, because that's one of the more obscure things. There's 2 nitrogens right here, so let's put a 2 there to balance it. That covers your nitrogen. There's 3 AS, what is that, arsenic? 3 arsenics right here. So I better put a 3 right here. That covers that. Okay, let's do oxygen next, I guess. There's 2 times 3 for 6 oxygen, 3 times 3 for 9 oxygen, which is a grand total of 15. Here there's 2 of them. Here there is 12 more, which is 14. But this last guy right here is number 15. So I think you just need a 1 there. And if this holds true, when I do hydrogen, hydrogen better also be even now. So let's try hydrogen. Hydrogen, there are 2 right here. Then there are 9 right here for a grand total of 11. This guy's got none. This guy's got 9. This guy's got 2. Hey, that's a grand total of 11. We're good. Last thought, were the charges balanced? This one here actually didn't require charges, which was kind of nice. But look, I just balanced it by looking at it. And that's why I leave this slide for last. Okay, I know I'm running out of time here. Give me 1 more minute, then you can go. This really is your in case of emergency, break glass. Oh my goodness, we need to do something. The 2 middle examples I showed you there, I really hope you don't ever have to do that on diploma. But it is an option if you cannot figure out how to balance it just by looking at it. Okay. The outcome I'm supposed to teach you guys, hopefully I've done that fairly well, is students know how to balance redox equations. Sometimes it's easy. You just look at it, you're done. Other times it is a pain in the butt. Okay. I do think you guys should practice this, by the way. So there is a worksheet on my website. So that wouldn't be a bad idea tomorrow. Okay, quick summary then. We've now covered our first 5 topics. I want to give you guys a work day tomorrow to kind of consolidate your knowledge, and we should try our first quiz on Wednesday. If I lost you, by the way, today, can you let me know later? And I'll try to do another example with you so that I can try to help that out. Because I know I only did 4 examples, but I'll do more as you guys need. Any questions? Okay. Not yet. All right, we'll see you guys later. It's basically 10 o'clock here, so you should get going.